Alrighty. Hey again, everyone. So now what we're going to do is we're going to actually look at expressing these different methods for solving our linear systems, right? In the last video, maybe I'll kind of recap here. So the different methods, maybe I'll just writing with a trackpad here, so I'm sorry if it's terrible. Kind of the different methods we're looking at. And again, this is to solve, what we want to solve is AX equals B, where A is, for the lab, like what we'll do is A will be 3 by 3. B will be a 1 by 3 vector. Right, and then so that means X is also a 1 by 3 vector. But, in general, we want to extend this to arbitrary size. We want this to be like, in general, we want this to be n by n, and this to be 1 by n, right? And we'll see that later, but for now, let's kind of go through these methods for solving linear systems with numbers that we're familiar with and comfortable with in lower dimension, namely like 3, right? And the 3 methods we're going to be looking at for solving this, the first one is the reduced row echelon form, right? And remember, what is reduced row echelon form? How do we go about solving this system using reduced row echelon form? Well, what we have to do is we have to set up an augmented matrix, right? We have to set up the augmented matrix A, B, and then we put this into, when we use reduced row echelon form, we get something like 1s down the diagonal. And so again, I'm using now, let's look at like 3 by 3, right? So the augmented matrix is going to be 3 by 4, right? And then so in the end, we'll have something like, in the 4th column, we'll have something like x1, x2, x3, right? And then we know if these are all zeros, we know that our solution vector is just the 4th column, right? And so that's what we see in the code over here. We'll get to that in a second. So if we want to find the reduced row echelon form of a system like this, first let me define some matrices. Let me define like A1, say. So let's look at A1. And I can just pick a matrix, for example, right? There's a given one in the lab. So when you're going through your lab, like your write-up, you'll want to make sure you want to input the numbers from the matrices of that. I'm using a different example here, just so we can see more numbers. So I'm using the matrix 1, 1, 1, 0, whoops, 0, 2, 5. Can put a space there if I'd like. And then 2, 5, -1. So here's my matrix A1. And then I'll have my vector B1. I want this to be 6, -4, 27. Okay, again, this is just an example. And if I want to solve the system like A1 equals, or A1x equals B1, what I have to do for the reduced row echelon form is I set up the augmented matrix, right? And so that's what M1 is doing here. M1 is my augmented matrix A1, B1. And then I can define another matrix S1 to be the reduced row echelon form of M1, right? So it's going to look something like this over here. And now I can define a variable x1 underscore reduced row echelon form to be S1 but it's not all of S1, right? What does this notation mean? This means I want all rows. So maybe I can write this, all rows and what does this 4 mean? It means the 4th column. And so this X1 RREF is actually a 1×3 vector, and it's going to be this over here, right? Maybe I can draw an arrow all the way through here. This is my vector, right? And you'll notice that X1 RREF is the solution to the system A1X equals B1, okay? So here maybe I'm using A and B for the sake of being uniform with notation. We can write this, right? A1, B1, okay? And so this is how we're expressing solving this linear system using reduced row echelon form, okay? So check. There's one. What was the next one? The next one we did was inverse. This is the next one that we'll talk about. All right, so go ahead and clear all this. And let me remind us, we are trying to solve A1X equals B1. Okay, and now if we want to solve this using an inverse, let's say we want to solve this using an inverse. Well, if we want to solve this using an inverse, we can say something like A1 underscore inverse equals, and what we want this to be is we want it to be X, right? We want this to be the solution, but in a different method, right? So if we do X1 inverse, well, how do we find this? What we do is we multiply both sides by the inverse, right? A1 inverse times A1 X equals, and with matrix multiplication, you need to be very consistent with which side you're applying the multiplication, right? If I multiply the left-hand side by the inverse on the left, I need to also multiply the left-hand side or the right-hand side by the inverse on the left, because we know more often than not, matrix multiplication is not commutative. B1 here. And so we know A1 inverse times A1 is the identity. So what we get is X is equal to A1 inverse times, maybe I can put an asterisk here, times B1, right? So this is another method we can use to solve this linear system. And how do we express this line here, right? What we want to do is take this line and express it in terms of code that MATLAB can read when we run this script. So I want this to be, whoops. I want this to be equal to A1 inverse. So I'm going to use the inverse function in MATLAB, or the inverse command, right? Inverse A1 times B1. Okay. And what this will get me is the solution using the inverse. And so, oh, looks like our methods got erased here. First one was reduced row echelon form. The second was inverse. And the third is this backslash operator. that we're going to use, right? And to use that, maybe we can call our variable, say, x1 div. For backslash, you know, we don't really think about dividing matrices, but when we're using a backslash, we'll say x1 div. And what do we want this to be? When you write, so I said this in the first video, but when you write a, if you write x equals a backslash b, this solves the system ax equals b. Okay. So what we want to do then is to define x1 div to be a1 backslash b, right? And so in doing this, or b1, sorry, b1. In doing this, what we have here, these three different variables should give us the same thing, right? Because we're solving the same system, and these are going to be integer solutions, right? So if you solve this system yourself, you'll get that x equals, so let me find what the solution turns out to be. The solution ends up being 5, 3, -2. Okay, and so since these are whole numbers and there's no round off error or anything like that, all three of these should give us the same result, and they should all be x if we did this right. So let's run the section and see. Okay, so quick error here. I forgot to take the transpose of B1, right? Because we want it as a column vector, not a row vector. So if I hit run, then this is what we get, right? We get our solution in each case. And we can look. So here, div gave us 5, 3, -2. Inverse gave us 5, 3, -2. x1 RREF gave us 5, 3, -2, right? And so that's exactly what we want. And again, because this system is nice enough, we get that all of these are the same. But in general, when the system is full of arbitrary real numbers, and these are, the solution can be filled with entries that take on infinite decimal places or have infinite decimal expansions, then these numbers won't agree to given round-off errors. And what we're going to do in the next video is compare the round-off errors, and then we'll also compare the time it takes to compute each one. So I will see you guys in the next video.